So, and now for the camera, I will take the point of view that you can think of these models that I will, why do I have this? So maybe let me go here. So I'm at this point now. I just reminded you of the ionization conjecture, and now I would look at other atomic models. So I have the atomic model Q. That's it sounds like a code word, but it just stands for quantum. So this is the atomic quantum model. Then there's the Hartree-Fock model, and then I will come to the reduced Hartree-Fock model and the Thomas Fermi model. And finally, I will also talk about something I call the mean field Thomas Fermi model, which is slightly different from the Thomas Fermi model and doesn't quite fit into the general picture. But in all the others, in HF, RHF, TF, and Q, I will be able to define an EZN, the ionization, and the radius. And then you can say, okay, maybe why are we introducing all these other models? Well, of course, to try to do something simpler, but also because they are good approximations to the quantum. So I will have two perspectives on these simpler models. They are approximations, but we can also study them in their own right. Because of course, if they're very good approximations, then any conclusion that we make about these approximate models would tell us something about the quantum model. But sometimes what it will tell us about the quantum model is not as good as what we know, but what we can actually prove for the approximate. The one example is that we can actually prove the ionization conjecture, the way it's written there. We can prove that for Hartree-Fock, reduced Hartree-Fock, and Thomas Fermi. We cannot prove it for quantum. And our level of approximation, the level to which we understand the approximation, that is not good enough to conclude the ionization conjecture for the quantum. Anyway, so I want to think of them both as approximations, and that's why I have a section here that's saying quantifying the approximation. So I will try to explain how good are these approximations at the level of the ground state energy. But I will also study them in their own way, and with a perspective and trying to understand the ionization conjecture. Okay, so let me go to the Hartree-Fock model. So there we go. So recall that what I did in quantum was that I looked at the quantum model was to look at all antisymmetric wave functions as functions of space and spin. So n, the function of n variables, each variable is a space and spin variable. I have n of those if I have n electrons in an antisymmetric square integrable. Now I make the huge approximation that I take a very special kind of antisymmetric wave function, what's called the Slater determinant. So I choose n orthonormal functions, and we refer to them as orbitals, inside L2 of R3 with extra parameters, I mean extra variables minus or plus, spin up or spin down, right? So it's R3 cross Z2, there are two more variables, and I'm looking at square integrable functions there, and I have n orthonormal. And for these functions, I define a many-body wave function, a correct, allowed many-body function. It's in my antisymmetric many-body space of n variables that is a determinant of the psi I evaluated at Vj, and then to have it normalized, you divide by 1 over the square root of n factorial. So it's an exercise to check that this is normalized. An easy exercise. Now, what I said before, and let me put that over here also, and I apologize again. That in the manifold quantum, we have the wave function stuff. This one is element in the antisymmetry. Don't see how I can write 12 or I can write how to do it. From this, we will get a what PDN. What are the densities in the star? This is a first class
operator on L2 of R3. That so this is the one particle, is an operator on the one particle. And to show that it was seen as an operator, the density meaning that it's a positive operator, positive operator. So I would have it. So that not occupy one time space, we go and then from the gamma prime, we got to the density of the rho prime. So the diagonal values of the first band operator something. So we have stars, gamma prime, rho, and actually the theory by which it's discussing, quantum mechanics uses to use the star. At the top level, that's the full complexity of the star with something. The other models try to describe it only in terms of gamma or even just the rho. The object that is described as an all-to-one level of potential. There's an abstract theory that is very different always described. That's it. That's this is for the ones that hold theorem, the physical rate theorem, but it's very, very constant, but has really tendency to the power 50 years. And given the Nobel Prize, but and the mathematical theorem is so much like relation. So the way to describe it is so complicated. That's like you basically have to go back and forth to form. Whereas the models, all the models cannot describe to the people. Now, all the known things, the models is called for the models, are actually things to the models to be about that. But now, first I will start to see that I'm going to get the gamma, this is the useful of the structure, down this. I will only do something but the simply the whole thing.
Okay, so the first theory is the Hartree-Fock model that I described as a Slater determinant. The reason I did this little show of reminding you of the psi gamma rho is because, in fact, this function depends only on the gamma. Let me try to explain why. So this projection, this many-body wave function has a one-particle density matrix. So if you do the prescription of the one-particle density matrix of integrating out all the remaining variables, it's a fairly easy exercise to see that you end up with the projection onto the span of the orthonormality. So the gamma of this is the projection, the n-dimensional projection onto the spanner. And in fact, this function here does not depend on how you choose this basis. I mean, it actually only depends on what is it called? The subspace. Now, this is true up to a phase, but in everything we do not really care about phase. Because, and that's what I'm trying to explain here, if you chose another basis for the same space, I mean, for the range of gamma, which is this span, then the new base, the old basis, I wrote that the old basis will be a unitary matrix acting on this new basis. And then when you calculate the determinant, it's actually a determinant of the product of the U times the old matrix you took the determinant of, and therefore the wave function of the old guy is actually determinant of U times the determinant of the new guys, the way I wrote it. But this thing is just a phase. So the psi actually depends only on the subspace spanned by the orthonormal basis of the orbitals, and that means it depends only on the gamma. So when I calculate the expectation value of the energy in such a Slater determinant, you should be able to express it entirely from the gamma, since everything depends on that. And this is fairly easy to do, and I wrote it down here. Well, the first terms are very simple because they explicitly depend only on the gamma. And here I actually wrote just gamma and not gamma psi, because I want to think of it now as forgetting the psi and only thinking of the gamma. That I'm now at the level of the theory that depends only on the one particle density. So we get trace minus Laplacian, 1/2 Laplacian minus z over x times gamma. Then we have, remember there's a density, which is just the sum over the densities of each of these functions. I mean, you sum over spin and you sum over the function, and the only variable is the x. You get an electronic interaction of the density with itself. That's called the direct term. And that's sort of what you would think if you had a continuous electric charge distribution. That's the self-energy of a positive charge distribution. But because each electron does not see itself, this is overcounting the contribution from the electron-electron repulsion. And actually, if you do the calculation, you will find that there is a correction to that. So this is a positive term coming from the electron-electron repulsion, but it's too big. And if you do the calculation, there's actually a subtraction, which depends again on the full gamma, not just on the density. So if you look at the matrix, or you look at gamma x sigma y tau, you square this sum over the spins and divide by x minus y and integrate here. We know that the sum of those two terms must be positive, because it's the expectation of the many-body repulsion, which we know is positive. I mean, it's not immediately clear that this thing here is positive, but it is, right? Because it's an expectation of a positive term in a Slater determinant. Okay, but you see immediately that there are terms that depend only on gamma. So there's a first term that's very explicitly just the gamma as an operator. You multiply by this one-body thing. That's what we call the direct term. And this last correction to overcounting, very explicit term, that's called the exchange term. That complicates this model a lot, because even in this model here, we do not know the convexity of it because of this term. So, and in fact, we will come to another formulation in a little bit that where I can even allow the gamma to not have, so here I guess I didn't write it, but recall, maybe I should put it over there, that the trace of gamma but we will actually see, I'll do it in a moment, that we can relax this and not just look at projections. Because the trace of a projection is always an integer, but it's the dimension of the space you project onto. But you will actually be able to relax it so that the trace need not be an integer. I'll get to this in a moment. And then you could actually have this curve be defined for non-integer values. And in that case, I don't believe the curve is convex. I believe it is convex if you restrict to the integers, but I do think it looks a little bit funny now. I think I had a proof of that at some point and then forgot to write a paper about it. And maybe it was even wrong. So I just don't know. But I believe it's not convex. But I do believe it's convex along. Okay, but let me get to this relaxed way of formulating the Hartree function. Remember that we had the conditions, I think I wrote it there, that gamma is between 0 and 1. Now, for a projection, we actually know much more. We know that the eigenvalues are either 0 or 1. 1 if you take a function from the span, I mean the range of the projection, and 0 if you're outside. The projection has eigenvalues 0 or 1. But we could think of, because for the true many-body thing, the one particle density matrix is only between 0 and 1. So we could say, oh, what if we took this functional that we had before, this thing here, and what if we allowed gamma to just be between 0 and 1, still have trace gamma equal to n? Would we have another function? Would something else happen when I calculate the n? And the point is, in fact, not. And that's a nice thing to know because it makes Hartree-Fock theory much more flexible to work with. So the statement is up here, and I should have put it as a theorem. It was actually proved by Leib many, many years ago. And Volker Bach found a very elegant proof that I'll explain here, again with a few details weaved under the rug. What does it say? Well, what we really want to define now is this ground state energy, EZHF. So now notice that I'm not putting the Q on top, I'm putting the HF up top because it's partially positive. So it's the infimum of a gamma being any projection, trace gamma being n of the functional that I had on the previous. That's the same as minimizing over all later determinants. I claim that I do not get anything different. I do not get anything smaller, strictly smaller, if I relax being a projection to saying that the eigenvalues are between 0 and 1. So let me prove that. So I'm proving this equality is a definition. That equality is what I want to do. Right? So the lower bound, that this thing is smaller, that's clear, because I'm enlarging the set on which I'm taking the minimum. So greater than or equal to is clear. What is difficult is the other way around. So I say, okay, we may restrict to finite rank. So this is something one should think about a little bit, whether that's really true over here, if you can really restrict to finite rank. I mean, if the approximation is still true if you do all finite rank. That's my sweeping under the rug. So I'm saying, okay, let's take something which is finite rank. M is no longer n because the sum over the lambdas is n, and each lambda is between 0 and 1. That means I'm doing this. And then I'm writing down again my many-body functional, the one I had there, expressed with a gamma instead. All the terms make sense. So I want to study it. And basically, I would like to study what is on top of the x minus y. Right? If I go back here, you see there's an x minus y there. There's rho gamma, rho x, rho y, and then the gamma there. There's a 1/2 on both terms. So if I forget the x minus y in the denominator, I have the rho minus the gamma squared. And that's the term I'm considering right there. I want to look at this. And I claim that that term is a matrix Aij lambda I lambda j, where every coefficient is greater than or equal. So let me get back to that, why every coefficient here is greater than. But now let's assume that we are doing the case there that the sum over the lambdas is an integer, but the lambdas are not 0 or 1. But then at least 2 of the lambdas must be strictly between 0 and 1, right? Because they have to sum out, if all of them except 1 was 0 or 1, then those would sum up to an integer, and then the last one, if they all sum up to integers, must also be an integer. So if they sum to something which is not an integer, at least 2 is cannot be integer. So there must be at least 2 lambda 1, lambda 2, say, it doesn't matter how I count, they were not ordered again, that are between 0 and strictly between 0. But that means I'm allowed to lower one and raise the other without changing the condition that they're between 0 and 1. Right? So I make a change of the gamma where an increase, I said increase, the delta here could be both positive and negative. Right? But so I could increase lambda and decrease lambda 1 and decrease lambda 2 a little bit, and I would stay where I was. And if you now simply plug it in, you will find, if you go back here and look, these things are, that's the term linear in lambda. Right? And these things are quadratic in lambda. Right? So when you now calculate the whole thing, you will get something that when you expand this, you have terms that are linear in lambda 1 and lambda 2 and that are quadratic. Right? So you will get in the delta a second order polynomial. And the fact that these aij's are greater than or equal to 0 means that the coefficient in front of delta squared is negative. So because it's a plus delta minus delta, so the term where you multiply the two would be minus delta. So if you want to do the best, if you want to lower the energy the most, this thing here is a concave function. Huh? So the best you can do is either to make the delta as small as possible or as large. But you don't want to stay between the 0 or the 1. So you could not have been at the minimum in this case. Okay, the fact, so I just need to explain why the aij is greater than or equal to 0, but that's simply writing out what it is in terms of the wave function. So you will see here, I wrote it out, that there's the thing coming from the rho. That's when you have I mean, here I'm summing over I and j, and here I'm summing only over the pair. That's why things come in twice. So I have the phi ix, phi jy, phi jx, phi iy. And there, this is from the exchange term. You write those out, and then it's simply like you see that this is a complete square, so it's greater than 8. So this was fast proof, and this is okay. So that's what I wanted to say about Hartree-Fock at this point. I should maybe mention that Lieb and Simon proved that there actually is a minimizer again when n is less than z. But I will come and review the properties are actually down here. Maybe I should have. I just want to say it before I go to the next model that we do know something about Hartree-Fock corresponding to what we also know about Thomson, and I will get to that. But I wanted to first introduce another model that's called the reduced Hartree-Fock model. I wrote a paper about this model many, many years ago because I wanted to try to prove the ionization conjecture there. And I couldn't prove it for Hartree-Fock. I struggled with it for many years. I could not prove it in Hartree-Fock, but then I figured out that if I ignored the exchange term, then I could prove it. So this is the same model, just with the exchange term thrown out. And then I had to invent a name for it, so I called it the reduced Hartree-Fock. There's something else that's sometimes called reduced Hartree-Fock, but it's better called restricted Hartree-Fock. And that's if you restrict in some way or other the orbitals that. I mean, in chemistry, it's very common to restrict to orbitals that are functions of space-time spin. I mean, saying that each orbital has either spin up or spin down. But we don't know that the best thing is to choose a function that space-time spin. Most likely, it's not the best to choose a function that space-time spin. And you can even restrict more. You can restrict to orbitals that have angular momentum, meaning that they are eigenfunctions of L squared or even of LZ done sometimes. But that's also not something that we would know for the true minimizer. So these may be simple for computations, but mathematically they give other theories than the usual Hartree-Fock. But actually chemists, they do know this. So they have something that they amend Hartree-Fock theory so that when they get to the very last, so they have these orbitals, and the very last orbital, so most of the orbitals that do restrictions I just described, space-time spin or angular momentum. But then they know that when they get to the last orbital, maybe there's some mixing going on. And then by hand, they do it for the last orbital. And this may actually be a correct thing if you minimize, could be much closer to the truth. They have all these rules, some of them known as Hund's rule, about how you should pick the last orbital. But this was just to tell you what is often meant by restricted Hartree-Fock. I'm still thinking of Hartree-Fock where I minimize over all possible functions. Reduced Hartree-Fock for me, abbreviated RHF, is a theory where the exchange term is real. This is much, much simpler because it's a convex function of the gamma. Right? This term is linear in gamma. Rho gamma is linear in gamma, right? Because it's just the thing where you take the gamma and you put in XX and sum over the sigma. So the rho is linear in gamma. This is linear in gamma. And this integral here is actually convex in rho gamma. So what it's known that because the Fourier transform of the Coulomb kernel is positive, the Coulomb kernel as a kernel, not also as a function. Coulomb is positive, but it also has positive Fourier transform. So it's a function so that this thing here is a convex expression in the densities rho gamma. So the whole thing is convex, not strictly convex in gamma, but it's strictly convex. This last term is strictly convex in the density. And this allows us to say that there is actually a unique density for the min. There may be several minimizers, although I don't quite think that's true. But the density at least is unique, and the density therefore must be a spherical symmetric function. And that was the reason why I could actually prove the ionization conjecture in reduced Hartree-Fock, because it's much easier to deal with spherical symmetry. And then about 10 years later, I was able to generalize it to Hartree-Fock. So I'll get to that down. No, they do not use reduced Hartree-Fock. But I will use it for other things as well. So chemists, of course, want real numbers. And you're not going to get real numbers by removing the exchange term. But they do something like reduced Hartree-Fock in the following sense, that when they do, I talked about density functional theories before, that are theories that depend only on the density. But chemists go a step further, and I will do that later on also. They actually, when they have a density functional theory, they often will also have what they call the Kohn-Sham theory. The Kohn-Sham theory is to say, oh, we have a lot of, for instance here, this term depends only on the density. But that term does not depend only on the density. That depends on grammar. This is the type of theory that a chemist would call a Kohn-Sham theory, because it has lots of terms that depend just on the density, but the sort of one-body part, you should not write that only as the density. That gives too many mistakes. You should write that as the one particle density, and then they call it a Kohn-Sham theory. And actually, what chemists usually do is they discuss what should be the correction, the exchange term. So in Hartree-Fock theory, we have this exchange term that depends on gamma. The chemist would not call this a density functional theory because this term depends on gamma. The chemist finds a term here that depends on the density. And they make up all kinds of choices. So they do use reduced Hartree-Fock in a sense as the common core to all their density functional theories. But they want to have terms here depending on the density. I should say that if you do that, again, you will usually break convexity because you will put in a term which is negative power of the density, an integral of a negative power, at least that, or even more complicated. So you would break convexity. Okay, let me just mention then. So this was a convex functional. We know that the density is unique. Now, so I again do exactly the same definition. I define the minimizer over all the gammas between 0 and 1 for this functional of the reduced Hartree-Fock. So now in quantum, in Hartree-Fock and in reduced Hartree-Fock, I have defined the ground state energy as a function of n. Right? And we can study everything that I wrote there, the radius, the ionization energy, and the maximum ionization. Right? So I can formulate the ionization conjecture in all of the models that I have described: quantum, Hartree-Fock, reduced Hartree-Fock. Now, okay, so I will come in a moment and compare the different theories. Let me now just talk about, I call it here properties 1 to 4 for HF and IHF, and I don't know why I did that since there are only 3 properties, but so I should have said that there are 3 properties for Hartree-Fock and reduced Hartree-Fock that are the same as in quantum. So this is a non-increasing function, For reduced Hartree-Fock, it is also a convex function. So now, finally, I have a model in which I can prove that that curve is convex. Now, I didn't mention it before, the number sign here just means that you replace this with a Q, HF, or RHF. Now, that this is non-increasing, I didn't mention it before. That's easy. That's an easy. I say that, but when you're actually writing down, it's maybe not that easy. The way you prove it is that if you first have calculated for some n, and you want to now show that it's less than or equal for adding an electron, the point is that you can add this electron very, very far away. And but you need to do a little cutting and pasting. Maybe you can cut down the thing you have for n that gives almost the right energy, and then you add an extra electron very, very far away. N does not, now I'm talking about the case when n is an integer. In Hartree-Fock and in reduced Hartree-Fock, n has to be an integer. It's in quantum and in Hartree-Fock, it does not have. But it's true, in reduced Hartree-Fock, it does not have to be an integer. You can still morally, I mean, in Hartree-Fock, you may say it also does not need to be an integer. You could relax it, but yes, I think it's less meaningful in that case, but you can relax it. But I'm thinking of morally adding an electron far away, meaning that you take your gamma and cut it out, and then the remaining part, which may not have integer trace, you put it very far away. And in that case, it's very easy to prove that this function is non-integer. You can make a trial function, but with more mass that has that does not have that has at least the same end. So that part. Now, minimizers exist for n less than or equal to c. So this was Ghislain in quantum. Lieb and Simon proved it for the Hartree-Fock theory. That's less easy because, I mean, existence of minimizers is easy when you minimize over larger sets, right? So in quantum, it was a linear minimization. Here, it's a non-linear minimization. But Lieb and Simon did that back in the 70s. For reduced Hartree-Fock, I mimicked what they did, and it was actually somewhat easier. So I proved it for the reduced. Minimizers do not exist for a greater than z plus a constant for Hartree-Fock and reduced Hartree-Fock. So that's part of the ionization conjecture, and this is something I proved back in 2003 for Hartree-Fock. And I'm saying here we will get to that later. I'm not sure I will get to it in these lectures, but I hope to maybe mention it at the very last lecture. That's the complicated proof where you prove that the n critical is actually z positive. And these IZ and RZM are defined as for the quantum model, and in Hartree-Fock theory, you can prove the bound there too. So I also proved those. Okay, so now let me compare the different models. And actually, this is not difficult at all. So we have the quantum model, we have the Hartree-Fock model, and we have the reduced. And it goes like that. Quantum is the smallest, then comes Hartree-Fock, then comes reduced. This inequality there is trivial because I'm just restricting the wave function that I'm using to find the minimum to Slater determinants. So I'm minimizing over a smaller set. So of course I'm getting a bigger n. Here it's a little different. Here I would remove the exchange term, which increases the energy. So that's why I do have an inequality there. But I also need to use this Lieb variational principle. Right? I have to say that, well, I mean, it depends how you define Hartree-Fock. If we have already accepted that Hartree-Fock is defined by the relaxation 0 less than gamma less than 1, then this inequality is also trivial because then it's just saying that I remove the part. Right? So then I have these inequalities. And I already mentioned this spherical symmetry of the density rho gamma. Now, the minimizers of quantum and Hartree-Fock are not necessarily spherical. Now, this is may sound a bit as a surprise. Are atoms not round? And no, they're not necessarily round. Atoms can have angular momentum. I mean, atoms can have total angular momentum, and that means that there's a preferred direction, the direction of the angular momentum. And that just means that the ground state is not unique. You can find a ground state that has a spherical density, but that is not a pure state for the quantum. For Hartree-Fock, in general, you will not be able to find one that is spherical. Okay, so I mean, one example for Hartree-Fock is just to look at hydrogen. In hydrogen, you might say, oh, the density is of course spherical, but it has spin. Right? So the spin is, you have to choose the spin either up or down, some direction of the spin of the one electron you put in. And then maybe the density is spherical, but the whole ground state, which is just one orbital, which is the same as for quantum, is of course not spherical because there has a spin that has to point somewhere if you want to make it a pure spin. And that actually complicates things a lot. I mean, I had to struggle for almost 10 years to prove this for Hartree-Fock because it did not have spherical. Okay, so let me briefly mention the variational equation for reduced Hartree-Fock because I want to get to that when I now start comparing. Maybe let me go up again. You may now ask, oh, okay, so this is bigger than quantum. But how much bigger? Right? If I really want, I mean, this could be a terrible approximation, right? And actually, it often will be, but I will argue that it's not so bad because I will give a bound that bounds the quantum from below by the reduced Hartree-Fock. So, but I just would like to discuss a little bit what is the sort of variational equation for reduced. So this is claimed here. Imagine that we have a minimizer. So if gamma really minimizes this reduced Hartree-Fock, but we've forgotten the exchange term. The same thing is actually true also for Hartree-Fock. It's just a little more complicated to state because what's called the mean field operator is slightly more. But what you do is you calculate what I call the reduced Hartree-Fock mean field operator. MF is for mean field, RHF is for reduced Hartree-Fock. And it's the operator which has the -1/2 Laplacian kinetic energy, attraction to the nucleus, and then you simply put in the repulsion from all the other electrons. Right? Remember, in reduced Hartree-Fock, I do not have an exchange term, so I'm overcounting the repulsion between the electrons. An electron repels itself. Right? But if you have lots of them, maybe it doesn't matter that much. So this is of the mean field operator. This is what one electron sees from all the other electrons. And what I'm claiming is that if you're minimizing this with a restriction that trace gamma is n, then there exists a mu, a chemical potential, so that this thing here is actually the sum of the negative eigenvalues, meaning the gamma is, I should be a little bit careful here, but let me first say something which is not quite true and then correct myself. This is almost saying that gamma is the projection onto the negative eigenvalues of that operator. Right? That's not quite true, because in principle, this operator here could have a zero eigenvalue. And if it has a zero eigenvalue, then I don't know how to put in the gammas. I mean, this will not tell me what I do with the zero eigenvalue. But then it actually, knowing that the trace of gamma is n and that you have spherical symmetry, you more or less know what you're going to do also in the last eigenvalue. But that I'm not including that. I'm just making this claim that the gamma minimizes this expression. The zeros, yes, this may happen. Just think of varying the z. At some point, an eigenvalue will have to disappear. Right, the number of electrons at some point will have to disappear. So it's not clear that they're actually eigenfunctions right at that point. So that's slightly tricky issue, but I think it may happen. Okay, so so let me prove this statement. This is fairly easy to prove. First of all, I mean, this thing about putting in a mu, this is the usual story about the Lagrange multiplier. Instead of having trace gamma equal to n, then you can put in a chemical potential and say that the gamma minimizes an expression like this without any restriction. You simply choose the mu as being the derivative. So you have a convex function, you subtract the linear function so that you're getting to be at a minimum. given the n that you're choosing. So that's a usual story when you do minimization with convex functionals in restrained minimizations, which turn it into non-restrained with a chemical, with a Lagrange multiplier, which I here call the chemical. Okay, so now let gamma prime be any other thing between 0 and 1. And then I just plug in a trial state, which is 1 minus alpha gamma plus alpha gamma prime. This thing will have the correct properties. And it's still between 0, eigenvalues between 0 and 1. And then I simply take a derivative of this because I know that gamma is the minimizer for the reduced Hartree plot. So at alpha equal to 0, this must have a positive greater than a derivative that's greater than R. And if you simply calculate this derivative, you find that it's exactly the gamma prime minus gamma of this expression up there, meaning that the gamma is smaller than anything else, and you could have chosen the gamma prime to be the true projection onto the organism. So we have such a restriction. And I'll come back to this variational principle for reduced Hartree plot. But just think about it for a second. What does it really mean? It means that I have solved the following problem. I have found the density rho, so that when I calculate this mean field operator that has all the electrons feeling all the other, an electron feeling all the other electrons, I have found it in such a way that when I calculate let's forget about this thing about 0 being an eigenvalue. When I calculate the projection onto the negative eigenvalues of this thing here with the chemical potential, then it's exactly the function gamma that I started. I have found a one particle density matrix gamma, so that if I calculate its density, write down the many-body, the mean field operator, then the projection onto the negative eigenvalue is the gamma I start. Right? So there's this self-consistent condition on the gamma that I have satisfied with this equation. Okay, now I would like to explain to you, and I hope I can finish it. I have about 12 minutes left. I would like to explain to you how to prove a lower bound on the reduced Hartree plot, on the quantum in terms of the reduced Hartree. It's not the best known, but it's one that I can do fairly easily. But I need one ingredient, and that's the Lipschitz inequality. So I hope you all know the Lipschitz inequality. If not, it's an exercise. And the exercise is like this: find a short proof in the literature of the Lipschitz inequality. And then, or you can also try to find one. I have what I think is a very nice short proof with Robert Zeiringer, who will talk tomorrow. You can look at that. There are other nice proofs of the Lipschitz inequality. It says that if you have a gamma between 0 and 1, and you calculate its kinetic energy, then it's bigger than or equal to the density to the power factor, the incident, with some constant, and the value of this constant is a big problem. What is the best value? I'm not getting into that. I'm just interested in the fact that there is. So I will be using this inequality. Let's go back to what we knew about quantum, that it was bounded below by a constant z squared n to the 1/3. That's there. I had it written over there. Now, that bound did not use that there was a 1/2. Well, it did use that there was a -1/2 Laplacian, but it would also have been true if I had written 1/4 of the Laplacian. Maybe let me go over here.
So the famous graph that we described, -1/2 Laplacian, I say -1/4 Laplacian. 1/4. It's not the greatest idea in the world, but it means that I can take, I have equation, a bounded continuation by a similar Hamiltonian with a smaller here, then I have saved the smaller equation already. Now, if I conclude the same lower bound, for the stem path to the one forward. Then I know this is actually a bounded by the time I would say from this that is and greater than the distinction minus the constant greater than one. Mine is one quarter from one. But it's also a revolution. Well, I proved that I had already proved
that the many-body operator was bounded below by z squared into the 1/4. That's also true if I had a smaller kinetic energy, I would just get a bigger constant. And then I have tested a little bit of mediation. Okay, so now imagine that we have a function, a wave function, that actually gives you negative energy that the whole quantum is negative. That means that the expectation value of the Hamiltonian plus this extra positive term of the Laplacian altogether must be negative. And if the term from the Hamiltonian is minus z squared into the 1/3, then the positive term cannot be bigger than that, because then you would have gotten a positive term out. So effectively, you get an upper bound on the minus Laplacian gamma from
that's what I meant by keeping the correlation. So for example, you can see that the Laplacian minus Laplacian gamma is smaller.
Which means that for the neutral atom, I will know in all the models I'm looking at that the quantum ground state integral 5/3, HF ground state to the 5/3, reduced Hartree-Fock ground state to the 5/3. These are all smaller than z squared into the 1/3 in the neutral case, so some constant from z to the 3rd. So I have an a priori bound on the kinetic energy in all the atomic models, which is of order z6. So this I will be using, and this is my main ingredient in trying to get a lower bound on the Hamiltonian in terms of reduced Hartree-Fock. So I have 7 minutes left, so let me go through the bound and maybe return to it on my next lecture again, because maybe a little bit too fast. But this is sort of a nice argument, and I tried to push it as far as I could here, and every power on the z's play an important role. So I'm actually taking the Coulomb potential, x to the -1. And I'm replacing it by another function. I'm bounding it from below by a regularized repulsion. So the 1/xi minus xj, I want to get a lower bound, so I'm bounding it from below by another function which is more regular than the Coulomb. And what is the function I use? Well, I sort of smear out the electron. I say the electron, instead of being a point charge, is a little ball. It's a little ball of some radius a that I will choose later on. So this is the characteristic function of a ball of radius a divided by the volume of the ball. So this is a function that has integral 1. So think of this as a charge 1, a delta function, but you smear it out to a radius a. Now take two of such balls, placed in different places, and think of what is their repulsion if you have these charged balls. If they are far away from each other, bigger than the radius 2a, well, then by Newton's theorem, you see it as though there was just charge at a point. You see 1/xi minus xj. That's Newton's famous theorem about, he used it for the gravitational field, but now we use it for the Coulomb. As they get closer, it will be 1/xi minus xj until the two balls touch. And when they start moving on top of each other, it becomes smaller than it was before. Because now they sort of one can even calculate it completely explicitly. You can try that as an exercise. And that's the function I've written it here using convolution notation. The WA of x is putting one ball at 0, the other one at x, and calculating their repulsion. So this is a function which is always less than or equal to x minus 1. That's why I can use it as a lower bound. And it has the property that it's equal to x minus 1 when x is bigger than 2. Right? That's when the poles do not overlap. Moreover, you can calculate that the Fourier transform of this thing here is greater than or equal to 0, because it's a convolution of two identical functions. When you take the convolution of two functions, you get the Fourier transform squared. Then there's an additional function that you're convolving, but that has positive Fourier. Right? So altogether, this has positive Fourier transform. That's one important property. And it has a finite value at 0. Because when you take the two balls and when you move them right on top of each other, it's just the self-interaction of a ball of radius A, and that's fairly easy to calculate. It has to go like 1 over some constant times 1 over A, just by scaling. That's the only dimension that is there. So the function WA of 0 is a constant A to the minus 1. Right? If you make the ball shrink to delta function, then of course this will go. Okay, so that's the lower bound I will use. The Coulomb repulsion I bound below by this function. Then I use that, and I'm simply now rewriting it as delta function. Right? I say, okay, this is the same as writing it as you sum over all delta functions, and you integrate one pair. What I do there is that I include the self-interaction. Right? I mean, here I did all different pairs, but here I'm doing all pairs. But that, of course, is a mistake that I have to subtract. This is the mistake when two balls are on top of each other. So this has a 1/2 NWA of 0, but it's fine now. It's actually a constant A to the minus 1, which I wrote down. This is a sort of the density when the particle, classical charge density of point particle. Then I choose any positive density rho tilde, any one. I mean, anything that has a finite interval, and I subtract it off, and then I make the correction. Right? So then what did I make as a mistake? I had the rho tilde with the rho tilde, that's written there. And then I have that's when I have two rho tildes, and then I have a correction when the rho tilde hits the W, hits the delta. I wrote that there. Right? So this was an identity smuggling in the rho tilde. And now I use that it has positive Fourier transform, because then this thing is positive and I throw it away. Right? And then I end up with this lower bound. And this is just an amazing achievement that we have made at this point. And I can't take full credit for it. I mean, I maybe try to streamline it a bit, but this goes way back. We have estimated from below and interacting in many body terms, xi minus xj by a one-body potential. So all the interactions are gone. This lower bound will give you a non-interaction. Here, these two things are just gone. So then I plug it in. The energy is bounded below by this term, that term, and this term, and everything is now non-interaction. It would have been so nice if this had now been the Coulomb potential. Right? Because then I would have had something that looks like the mean field problem. Okay, let me not, since I'm really running out of time, I will come back to that, because you can estimate the difference between this and that. Not very difficult, it's just Hilbert's inequality. And then you conclude that you can get a lower bound in terms, you get an extra error term, and this is where I use these 5/3 norms. Right? I'm assuming now that I choose a rho tilde that has finite 5/3. But then you get a mean field operator here, the minus 1/2 rho tilde, and you get these errors. And rho tilde could be anything at this point. You choose the best rho tilde you can imagine. Right? Of course, there's a point here, how big an error do you make? But here you simply estimate it by that the best thing to do is something that's bounded by z to the 7th. So if you want to be close to the true rho, so this is, you don't really worry too much about that. What's really the question is, how do you choose the best choice of this? And I want to argue next time that the best choice is the reduced Hartree-Fock minimum, simply from the variational principle. You can almost see it when you think of now doing a variational problem here, the best you can do is reduce Hartree Fock minimizing. And then it doesn't take much to, but I'll come back and do it again later on, but let me just give you the answer. You will end up with the fact that this thing here is bounded from below by the reduced Hartree Fock of the gamma that you had. And you'll end up proving that the quantum is greater than or equal to reduced Hartree Fock with the power z to the 7th. I'll go through the remaining calculations next time. The really important thing here, for some of the things I want to talk about later on, is that I'm doing this is better than 2. Because I want to do a little bit better. But you can do much better. You can actually prove 5/3. That's much more complicated than the proof I did. Here, I worked hard to get it below 2, but the true answer that you can get right there is actually big O of Z5. Now, that takes much more work. This was done maybe the first time by Pfefferman and Secco. Then Volker Bach gave an argument, and then Graf and I gave another argument to prove that you can get down to big O of Z5. I will not go through those arguments. We will not really need them, but I want to review certain things that are known. Because to do better than Z5/3 in the lower bound, one has to now include the exchange term. It turns out that the exchange term is of order Z5. So if you want to calculate for large Z, so if you want to do better than Z5/3, you have to do the exchange term. And that's actually what Pfefferman, Bach, and then Graf and I proved, that you get a lower bound here, which is better than Z5/3, but then you have to include true Hartree Fock and not just reduced Hartree Fock. So thanks a lot for your attention. I'll come back to this calculation next time. Yeah. Oh, sorry. That's a funny thing. There, sorry. Yeah. There's a norm 5/4. There. Yeah. What? Yes, I heard this inequality. Yeah, the powers. So if I do the inverse powers, 3/5 plus 3/5 plus 4/5 is 10/5, which is 2, meaning I have 2 volumes in total when I do these norms. And here I also have 2 volumes. And this is using Hilbert. I used that it had positive Fourier transform. Mm-hmm. Well, if you use Yukawa, that only makes life easier. Because Yukawa is even not long range, and it still has positive Fourier transform. Right. So in fact, here I have to fight. I don't want to put in Yukawa because then it looks like I'm cheating in this. Well, I mean, you would maybe, I don't know where you would. If you studied the nucleus, you would maybe use Yukawa. That's much more difficult because, sorry, much easier because we do not have the long range. So the hard part is really understanding the long range. And maybe I could say that briefly that part of this thing here, I mean, you sort of cut, you do an approximation, a lower bound, by something which is more regular at the origin, but you do not change what's happening at long. That's the thing. Yeah, but it's depending a little bit of what you want. But I mean, if you want things uniform in the mass in the Yukawa potential, then you again have to do it, right? If you are happy with bounds that depend on the M, it would probably be almost like this. You would still have to, because here I'm regularizing the short range. This you still have to do for you. Yukawa still goes like 1/8. x, at small x. It's only at large distances that it would. So I think at this point it would not make it. Yes. I was going a little bit fast because I did not finish the argument, but here at this point, and I wanted at some point I want to use. I wrote an estimate there, but I want to use this estimate up here. I want to use that estimate if you choose the true many-body wave function there. And therefore, the rho that I have here is the rho coming from here. I wrote it down sort of as a general inequality, but I want to use the rho coming from the rho psi, which is the true minimizer. And there I want to use that it behaves like v to the that I have a bound from the Nietzsche. And that's the only place I use it. Well, that's not quite true, sorry. Because the rho tilde I said I was going to use as the reduced Hartree-Fock minimizer. And there I also use that has a bound of z5 first. And that's why down here, you see, it became 14 over 5, right? Because there were 3/5 and so on. It's the 5/3, the integral to the 5/3, which is the 7/3. So the 5/3 norm is 7/3 to the 3/5. It's 7/5. There were 2 of them. That's where you have the 14/5. One should not do calculations like that in public, but I think I got it correct. Yeah. And then you have the A, which was a free parameter, but that you just optimize, and then you end up with the 7/4. And the thing you really want is just to be better than 2. And I explain why I need better than 2. So this is for just this lecture, because we do know that it's z5/3, but that will require much more work. And it's nice that for a fairly simple argument takes you better than